action function on surface.
Okay, and thanks a lot for the invitation, and happy birthday to parties. I choose the topic, the action function on surfaces, because this topic is parties give me when I was a PhD student of his. Okay, now first we recall the classical action function. We suppose that M is a symplectic manifold. For simplicity, we suppose that the second fundamental group vanish. Okay. Let H be a Hamiltonian. The function is smooth. Then we can get a smooth isotopy. I denote it by I. We suppose that the F is the timer map. Then we can define a function on the constructible feed point set of F. Here, this is a subset of feed point set of F. That means if X is this set, then the trajectory of I is constructible on the manifold. Okay, the action function defined in the following. If X is this set, then the action function of X equal to here dx is any immersed disk on the manifold, such that the boundary of dx is the trajectory of x. That means Tx when t from 0 to 1. Okay, this is the classical action function. This one is important invariant in the symplectic geometry. Now we go to the. Now we want to consider the C0 case. Now we suppose that M is a surfaces with M is a closed surfaces with the genus is more than 1. Now we give on the manifold on the surfaces isotopy and a measure mu. The isotopy I write it like this. For simplicity, we suppose that the measure mu has no atoms and has full support on M. Okay, now we define what is the we call I is a mu Hamiltonian. Here we suppose that the time map F is F, and the map preserves the measure mu. Now we call I is a mu Hamiltonian if the rotation vector of the measure mu is 0. Here is the rotation vector on M. If F preserves the measure, then we can almost everywhere on M to define the eigenvector, the rotation vector. Okay. We say I is a mu Hamilton if the integral of the rotation vector is 0. Yes, we suppose that the genus is more than 1. And on the surface, this one is always 0 because it's contractible on. Here is the rotation vector. Because we have isotopy I, and we can almost everywhere point to define the rotation vector. But I think I have no time to explain what is the rotation vector.
The rotation vector is something in homology?
In homology. Yeah, in homology, this one in this set. So to look at the point and the isotopy, how to rotate around the manifold. Yes, like that. Okay, I have to continue. Okay. In the following, here I note that in this case, the second fundamental group is 0. Okay. In the following case, we can generalize this classical x function to this case, to this case, this setting. Now I state the theorem. Okay. Now we suppose that I is a mu Hamiltonian. And I satisfy the Darby property. Later I will explain what is the Darby property. Then we can define an action function on the contractible fin point set of F, which is generalized of the classical one. We denote this x function as maybe a mu. Now I play what is the Darby property. Here we have the surfaces, the surface and the isotopy. The isotopy F0 is identity. Here. And the isotopy and the timer map F and the measure mu and the contractible fit point of F. We lift everything to the unit quantum space. Oh. Here. Yeah. We lift everything to the unit quantum space. Tilt, I tilt. F tilt, U tilt, and this lift it is a feed point of F tilt. For any X tilt, Y tilt in this site, you can define the linking number between x tilde y tilde. I denote it by Li x tilde y tilde. We call the isotopy I satisfies the WB property on x tilde if there exists a positive number, an x tilde. Maybe here I note the isotopy. Later I will use this. A positive number so that the linking number x tilde y tilde is bounded above by this number.
I'm sorry.
Here I explain what is the WB property. WB property, I write it weak boundedness property. Yeah. Here we have this one. The setting we leave everything to the unicorn space. Okay. Then for any f tilde y tilde of the free point of f tilde, because we leave the isotopy, we get isotopy I tilde. So you can define the linking number of f tilde and y tilde. I denote it by this. Okay. We say that the isotopy satisfies the WB property on x tilde if there exists an x tilde, a positive number, so that this one, the link. Yes, a positive number. Yeah. So that the linking number is this one is less than this one, and for any y tilde is not x tilde. This is the isotopy, yes. But when we suppose that I is mu Hamiltonian, the WB property doesn't depend on the isotopy.
So you're saying that you may have different boundaries or different fixed points?
Yes. The I tilde will change. Yeah.
And it can be unbounded in the different points.
Yes. That this function maybe go to infinity when I tilde change. Yeah. We see that the isotopy satisfies the WB property if I satisfies the WB property on every point of on this side. Okay, that means here I write here. I satisfy the WB property if I satisfy the WB property on every point. On the field point set of S. Okay, this is the WB property. On this hypothesis that I is mu Hamiltonian and I satisfy the WB property, we can generalize the classical action function. Now I give a note that Foucault proved the following. I denote, for example, if I satisfy the WB property on x tilde, we also say that I satisfy the WB property on the project x tilde. Pi is the Torsion map. Okay. We denote all of the WB property of I as proved the following. The W property point is dense on the contractible field point of F. By the way we generalize the X function, we can prove that the following theorem. If I is a mu Hamilton, then we can define an X function on the WB property point set. That means we can define the X function on a dense set of the field point of controllable field point set of F. Okay. There's a classical result by Schwarz in 2000. He proved the following. Schwarz theorem. In the classical setting, if F is not identity, then there exists X and Y in the contractible field point set of F so that the X function is different. This is a classical theorem. We can further to generalize this theorem to the C0 case on the surfaces. Under the setting, the first setting, here I write it theorem 1, here is theorem 2. On the theorem 1, we can generalize this Schwarz theorem. Recently, joint work with Friedrich, we proved the following. In the setting, theorem 2, we can generalize the Schwarz theorem. But here we work in progress. Now we use, for example, we will to show. I will show how we applying this theorem. What we can get results by applying this theorem. Okay. We can prove the following result. Theory. If I is a mu Hamilton and the contractible field point set of F is connected. In particular, the field point set of F is connected. then the Taiwan map F must be identity by using the zero swatch theorem. Okay, and we can. Because yes, if this is connected, because this set is a open and closed subset of this set. So this set will be connected. Yes, this is the hypothesis. Then we can imply this. Okay. Okay, right.
I don't know why I understand because that will be identity.
Because the proof that.
You say the set of compatible fixed points connect, F is identity.
Yes.
Okay, so fixed point of F will connect. So it doesn't seem so obvious that it's true if you don't prove that it doesn't. The other way around.
If the fixed point set of F is connected, then
in particular, in the set of fixed points.
Yeah. Okay. The number of this set is less than 3. Then the periodic point is infinity. Here 3 because this is the cup length of the manifold. Here because the cup length CL m equal to 3. So we have this. The last result is the.
In that case, we get non-contractible.
Here.
Can you say yes? Can you say that this set
Okay.
non-contractible variable is
Yes, I think. You mean non-contractible fixed point set? I don't know. Contractible. Oh, contractible fixed point. For example, if I is 1, then F is identity, of course. Yeah. If is 2, because it's 2, then we can use the partition theory. Then the affiliation got 2 single points. Then the manifold is the sphere. So this case cannot. Yes, because we suppose that the fixed point set is finite, so we can use the partition theory. Yes, finite. We suppose this one, and use your. I mean that how to prove this theorem. I think here not periodic. 6 points. Sorry. Maybe star is better. Yes. Yes. I'm sorry. I new wrong notation. Okay. Now I introduce the next result. the continuity of the eigen function. This work with Verheidenhig and Sabhan. I forgot his name. Okay. The continuity of the eigen functions. Now we suppose that we have a sequence Hamiltonian. Yeah, I will. Okay. Yeah, I think I can do it. Fn is a C0 converted to F, and Fn is all of this is a Hamiltonian. Maybe mu Hamiltonian. We suppose that Xn and Yn is a free-point set of Fn. And we suppose that Xn converts to X of F. And Yn converts to Y. And we also suppose that, recall that the ∆B property, we introduce a notation, I, X2. If we suppose that all of things, In is respect to the isotopy of Fn, Xn and Yn, this one is uniformly bounded. Then we can get that the Xn difference mu Fn Xn minus mu Fn Yn converts to the eigen function of f x minus f y. Okay, I will stop here. Okay, thank you.